Hello, everybody. Welcome. I'm glad to see you all here. And let's see, I would like you to tell me where we left off last time. I have the chat up. Cool. Great. So yeah, we learned about Lewis structures last time. That's where we left off. So how's everyone doing, by the way? How are you? You can tell me what's going on while I share my screen. Good. I'm glad to see you're well. I know it's stressful right now. Okay, so you're right. We were going over Lewis structures, and here is what we left off with last time, drawing the Lewis structures. The key for this part down here for practice and homework is up on Canvas. If you haven't seen that, you can soon. And Lewis structures tell us what's bonded to what, which atoms are bonded to which, how many lone pairs, if there is a double, triple, or single bond between the atoms, right? It's a theory that predicts how atoms are bonded together. But it doesn't tell us the whole thing. All it tells us is the shape in 2 dimensions, how we write it on the paper. But we're going to learn today about the shape of molecules in 3 dimensions. And there is a theory called VSEPR theory. It's an acronym, VSEPR. It's not like Vesper, like the car, or Vesper, like the cocktail. It's an acronym that stands for valence shell, electron pair, repulsion theory. And what this means is that electrons that are valence electrons that are in either bonds or lone pairs, they repel each other, right? Electrons are negatively charged, and so like charges repel. And this tells us that the molecule will assume a certain shape that allows for maximum distance between the lone pairs and atoms. So valence electrons in bonds or lone pairs repel and maximize distance between them. And so this tells us the shape of the molecules in 3 dimensions. And so shape is really important. Remember, we talked about the central theme in chemistry, one of the central themes where structure determines properties. And this is a great example where the Lewis structure can tell us about the shape. And once we know about the shape today, we can know more things about how, say, for instance, if the molecule is polar or not, if it can dissolve in water, if it would have a really high boiling point or a really low boiling point, perhaps be a gas or a liquid or a solid at room temperature. Shape can also tell us really important things in biochemistry and biology as well. So the way that things smell is based on the shape of the molecule only, the way that enzymes work, and if there are drug interactions or if drugs inhibit, or if other molecules can, change the way enzymes work. It all has to do with shape, right? Molecular shape. So it's great that we are learning about it today. And let's see, so it all comes down to how many groups are on the central atom of a molecule. We define group as a bonded atom or a lone pair on the central atom. So a group can be a bonded atom on the central atom of either a molecule or of a part of a molecule that we're focusing on, or it can be a lone pair. So on this molecule here, how many groups are there? I'm going to highlight this in red. On this central carbon, how many groups are attached, either bonded atoms or lone pairs? You can tell me in the chat. Cool. So yeah, I'm seeing lots of numbers. Okay, good. Lots of participation. Thank you. And okay, I'm seeing 4 is a number. I'm wondering if you're thinking of actual number of bonds, right? We look over here, it's bonded atoms, not how many bonds are on the central atom, but how many bonded atoms. And when we look here, are there any lone pairs on that central carbon? There's no lone pairs on that central carbon. So what we can do is actually highlight that one oxygen is a group and another oxygen is a group on that central atom, right? So 2 groups. Of those 2 groups, 2 of them are bonded atoms and there are 0 lone pairs on that central atom. All right, so I have a model here that can help us see this in 3 dimensions. So this is a balloon model that I'm using to represent carbon dioxide. And so here's carbon in the middle, right, with the 2 oxygens right there. And if we squish it together, right, so if this molecule were squished like this and it wasn't out flat, there would be potential energy introduced there, right? Those balloons want to repel, just like the electrons in the bonds want to repel. So this is actually the shape of carbon dioxide in 3 dimensions. If we were to figure out the bond angle, what would the bond angle be between the oxygens, right, with the central carbon there? What's the angle between these balloons? Right, yeah, it's a straight molecule, right? It goes straight across. So this is actually called linear molecular geometry, linear shape, just like in Spanish, línea, right, means line. So it's in a straight line with a 180-degree angle. So we call this molecular shape linear, and here's the bond angle, 180. So I'm drawing, ooh, I'm drawing this in pink here. Hopefully you can see that difference, but here's the bond angle. And the molecular geometry, we said the shape of the atoms is what we call the molecular geometry. The shape of the atoms is called linear. And this is the shape of the atoms in the molecule. Next time we'll talk about the shape of the electrons and the atoms in the molecule, which we call electron geometry. But today we stick with just the atoms, okay. So what do we think? Let's do, want to try nitrate? Try the next one down here. Let's see what the shape will be in 3 dimensions. So again, the first thing we want to do is figure out how many groups are on this central nitrogen. And remember, this resonance structures, we can just choose one. It's all the same, just changed different locations of the lone pairs and double bonds, right, of the pi electrons. So we can choose one here. How many groups are on a central nitrogen? Right. There's 3 groups on the central nitrogen. And are there any lone pairs, or are they all bonded atoms? Yeah, they're all bonded atoms on the central atom. 0 lone pairs. So let's take a look at what this looks like here. I've got my balloon model, right, with nitrogen in the middle and 3 oxygens here. So if we kind of squeezed it together like we drew the Lewis structure, we'd see that these balloons up top want to kind of pop up, right? That's introducing strain, right? And crowding. But in 3 dimensions, they pop up. So instead of having it being 180 degrees on top with 90 degrees on the sides, what is that angle between the balloons there? Right? If we think about this as a circle divided in 3, like 3 slices of a pizza, what's that angle? Yeah, 120 degrees. And since there are 3 groups attached, we call this trigonal, tri, right, for 3, and we call it trigonal planar, right? In Spanish, plano means flat. So trigonal planar means that this is a flat molecule, meaning if we were looking at a plane, right, going through the molecule. So if we think of my hand as a plane, right, it's going straight through the molecule, right? There isn't one atom up top or one atom down below. It's all in one plane. So trigonal planar. We call it. And the bond angle is 120 degrees, like you told me. Oops, I drew that in red. That's okay. So trigonal planar. And the way that we draw this now, right, is by representing that shape. So the nitrogen will be in the middle, and it doesn't matter where you put the double bond or the single bonds to the oxygens, remember, as long as you have the correct number of lone pairs there. So that'll be my single, or that'll be my double bond, and I'll do my 2 lone pairs there. Single here with 3 lone pairs each. Right, 2, 5, 6, making an octet, and we've got our bond angle of 120 here for nitrate, and that's the same bond angle everywhere. If the atoms were different, so if this were not a symmetrical molecule, then we would see different bond angles because different atoms have different sizes, which can affect the bond angle, and as well as different electronegativities, which can affect the bond angle, as well as the bond distance, and so that'll affect the bond angle as well. So we've got another example. Let's see, trigonal planar here. What about ozone? How many groups are on the central oxygen of ozone? And by the way, if we're highlighting groups, so can you tell me? We had 1 group here, 2 groups here, 3 groups here. So how many groups do we have on the central oxygen here? Right, we've got 3 as well. 1, 2 in a lone pair, and 3 in each, right, bonded atom. So we've got 3 total, 2 bonded atoms, 1 lone pair. So let's look at the model. And I have used now an orange balloon to represent the lone pair to show that it's different from the bonded atoms. But it still takes up space, right? We're still seeing this balloon, this lone pair, taking up space. So we drew it like this in the Lewis structure, right? We drew the 180 degrees on the bottom and 90 on the sides, but when we let it relax, we see that the balloons repel each other just like the just like the atoms, or just like the electrons in the bonds would, right? And the electrons in the lone pair also repels. And it just so happens for this shape, which we call bent, this is a bent 120 shape because the atoms in the molecule take a kind of angular bent shape, like your elbow, right? Bent. And it turns out that the lone pair actually takes up more space than the electrons in a bond would. That's because it's not tied up in a bond. Those lone pair electrons are free to move about the orbital. So they take up more space. And so what's that going to do to the bond angle? What do you think that's going to do to the angle between the atoms in the molecule? I want to see what you think. Can you tell me in this concept check what you expect the bond angle to be for ozone? Do you expect the bond angle to be 120 right here, 180, greater than 120, or less than 120 for this ozone molecule? Or do you not know, which is fine too. So I'm going to start the poll. So I'm starting the poll now so you can log in your answer. And if you're watching the recording later, you won't be able to see the poll, but you can still participate and check back with me later. We're going to go over it in a second, so you can still participate. Okay, so let me know what you think. I'll give you a little bit here. It's my mask. Okay. A few more seconds. Good. Okay. So let's see, I'm gonna stop polling now. And good, so, okay, about, a few of you said, we got, majority of people said less than 120. We've got about 30% saying 120. Some people are saying 180. Okay, so if you chose D, less than 120, you were correct. Nice work. So the lone pair, like we said, takes up more space. So it actually crowds the atoms and pushes them down. We can see that on this picture that I drew here, right? The lone pair crowds those atoms. And so we see that the bond angle for this bent 120 molecule is less than 120, 116.8 degrees. Oops. And so let's write that in our chart. So for all bent 120 molecules, the bond angle is less than 120. Oops, that is a 1 in there, less than 120. And we call this bent 120 because the atoms in the molecule have a bent shape, and it is still 3 groups, so it's still within the 120 group. So we would draw it like this. I'm not going to draw the lone pairs on the oxygens on the outside. In the interest of time, I'm just going to show the lone pair on the oxygen in the center to show that, and we can show that the bond angle is less than 120 here. And we said it was 116.8 degrees. Okay. So we're going to continue next time. There's a lot more shapes to go over, a lot more fun to be had, a lot more balloons. And so if you have questions, ask me in the chat and we'll continue, but I'm going to end the recording. So I'll see you next time, everyone.